Hello AP Physics students, this is Dr. Brenzi, and this is a video continuing a video I made on position and velocity, and now I want to actually start talking about acceleration with two dimensions. One of the first things that I want to talk to you about is the average acceleration vector. So we know from a formula here that the average acceleration is equal to the change in velocity over the change in time, and that's something that we learned in Unit 1 when we were talking about one-dimensional motion. But now you'll notice that this also applies to two-dimensional motion with vectors. So let's figure out what the change in the velocity vector is and then divide that by the change in time. And that's how you compute the average velocity vector. Or excuse me, average acceleration. Sorry about that. So we need to figure out what the difference between V3 is minus V1. So I need to make a copy of the opposite of V1. So now I have a velocity vector in the opposite direction. And then I'm going to move that over here, put it on the tip of V3. There it is. And the result is from where I start to where I stop. So it is going to be a vector that is pointing straight down. So that is V1 minus V3. Oops, that's V3 minus V1. Sorry about that. I goofed it up. Let's fix that. V3 minus V1. That's the vector V3 minus V1. Okay, sorry about that. So that's a vector that's pointing straight down, and hopefully that makes sense, because when we have something that is in the air and no other forces are acting on it, we should have an acceleration that is pointing in the downward direction. Now, to get the average acceleration vector, we need to take this vector, V3 minus V1, and multiply it by a scalar, 1 over the change in time. So this scalar doesn't change the direction of the vector, it only changes its size. So we are going to get a vector that's still pointing down, it's just not going to be the same scale as this vector right here. So our average acceleration vector is pointing down. Does that make sense? Well, let's see here. Let's think about averages here. So if I were to make 5 free throws in a game, and I were to do that 5 games in a row, well, what would be my average? My average free throws per game is 5, right? So if I know that the acceleration is always pointing downward and it's always the same value, negative 9.8 meters per second squared, well, that's what this average acceleration vector should be as well, because it's always the same acceleration no matter where I am along this trajectory for the football. So that does make sense to me. Now let's talk about instantaneous acceleration. So I just said that at any point along this trajectory, gravity is the only force acting on it, which means it is experiencing an acceleration in the negative direction. And we know that the size of this acceleration vector from Unit 1, that the size of that acceleration vector is negative 9.8 meters per second squared. And that acceleration vector takes place, or is applied, everywhere while the ball is in flight. So no matter where the ball is along this trajectory, the acceleration vector is always, always, always going to be pointing down. Okay. One very common misconception, by the way, is that when the ball is up here, that there's no acceleration. And that's not true, and I'm actually going to show you why that's not true later on in the video. What's actually happening here is it still experiences an acceleration down at negative 9.8 meters per second squared. If you think about it, if there were no acceleration right here, well, this velocity vector wouldn't change, which means that this ball would just continue to fly to the right. And we know that's not what happens. We know that doesn't happen in real life. The ball comes back down. So there has to be some acceleration here at the top, and it is pointing back in the downward direction. Now we also know from human experience that when we throw something up in the air, like if somebody hits a pop fly or if the punter punts the ball, we know that along this part of the trajectory, the ball slows down. It gets to a point where it is only traveling in the horizontal direction. It has velocity in the horizontal direction. But when it starts to come back down, it speeds up as it does so. See? Hopefully you have an intuitive sense of that. Well, let's see, what does that mean? In other words, I have an acceleration vector that's always pointing down. I have a velocity vector that's always tangential to the trajectory, which is what I said in the last video. Well, what about this arrangement of these vectors can I say causes the ball to slow down? After all, now I'm dealing with vectors in 2 dimensions, right? So I can't just like add and subtract. And what about this arrangement of vectors, velocity and acceleration, causes the ball to speed up? Or can I make sense of how this acceleration vector causes the ball to actually speed up, whereas this acceleration vector causes this ball to slow down? Well, let's take the point where it is starting to come down and starting to speed up. What I can do is I can actually break this acceleration vector down into 2 components. I can break it into a component. Whoa, what happened there? That's not what I was expecting here. Sorry about that. I got a little confused there and I had to pause the video. But anyway, so as I was saying, I can break this acceleration vector down into 2 components. I can break it down into a component that is parallel to the velocity. So wherever this velocity vector is pointing, I can make a vector that is a component of this one, but is parallel to this vector, the velocity vector. And then I can make a perpendicular component at a 90-degree angle. And if I add up this parallel component plus the perpendicular component, I will get my acceleration vector. Okay, well that's nice, but so what? Well, it turns out that this parallel component is what changes the magnitude of this velocity vector, but it doesn't change its direction. All that this parallel component can do is make the object speed up or slow down. It can't change its direction. So if I have an acceleration component, a parallel component of acceleration, and the velocity, if they point in the same direction, then the magnitude of this velocity vector is going to get bigger, which means that it's going to increase in speed. So that's what we have here. This object is going to speed up because this parallel component of the acceleration is parallel, pointing in the same direction as the velocity. So over time, this component of acceleration is going to cause this vector to grow in magnitude. On the other hand, let's look at the other part of the trajectory where we were saying it slows down. So this was our velocity at the moment it was slowing down. Our acceleration vector is still pointing down. And I can break down this acceleration vector into a component that's parallel to this velocity vector and add to that a component that is perpendicular, and I will recover my initial velocity vector, Well, in this case, the parallel component is opposite of the velocity, which over time is going to cause this velocity vector to shrink. So the magnitude of this velocity vector is going to decrease. So when you have a parallel and velocity pointing the opposite directions, then the magnitude of the velocity decreases. And when the magnitude of velocity decreases, that means your speed is decreasing. So this is slowing down. So the arrangement of the acceleration and the velocity determine if something is speeding up or slowing down. What does this perpendicular component do, this vector in red? Well, it turns out that what that vector does is it changes the direction, but not the speed. So this red component, the perpendicular component of my acceleration, that is not responsible for changing how much this grows or shrinks, but it does change which direction it's pointing in. So what this vector is telling me, this perpendicular acceleration vector is telling me, is that over time this velocity vector is going to creep more and more toward this direction, which means that this particle or this object, this football, is going to follow a path that curves in toward the acceleration vector. So it is going to keep curving in, and I've exaggerated this. This isn't the path that a football would follow, but I wanted to exaggerate this to show you the curvature, the fact that this is curving in. Likewise, over here, I had a perpendicular component that points in this direction, so as this ball is moving up, it is going to curve in towards that perpendicular acceleration vector. And so it will curve in similar to that. Again, I've exaggerated this because I want you to see that curvature. Okay. What's happening, why this doesn't happen in on a real football, why don't we see it go around in a tight spiral like this, is because as we are moving along in time, this velocity vector is changing both direction and it's changing magnitude. So this points in this direction at this instant, but later on it's going to point in another direction, and later on it's going to point in another direction. So even though the acceleration vector is constant, the fact that the velocity vector changes causes this acceleration to do different things to the ball at different points in time. So I want to finish up this video by let's take a general path. So let's say that there's a particle on a general path that goes from here, and it follows this trajectory right here. Well, it's not a trajectory, but it follows this path right here, and then it ends up right here. So this is just like a general path in a two-dimensional plane. In addition to that, I'm going to say that on this part of the path, our little particle speeds up, and on this part of the path, our particle slows down. So I told you in the previous video that the velocity vector, oops, I forgot to tell you this. Let's say I want to draw velocity and acceleration vectors at 5 different points in time. 1, 2, 3, 4, 5. So let's first of all draw the velocity vectors, and I was about ready to say that the velocity is tangential to the path of motion, so my velocity vectors are going to point tangential to the curve, to the path, and since it's speeding up over here, that means my velocity vector magnitude has to be getting bigger and bigger. So I'm drawing velocity vectors that are growing in size. And over here, since we are slowing down, that means the magnitude of my velocity vector has to decrease. So that's what my 5 velocity vectors would have to look like. Growing over here, shrinking over here, and always tangential to the path. Now acceleration, I know that it's speeding up over here, which means that the parallel component of my acceleration has to be pointing with the velocity. So with the velocity, Right here I'm going to assume it's neither speeding up nor slowing down. It's actually transitioning from one to the other. So I'm not going to have a parallel component of acceleration here. Over here, we're slowing down, so now my acceleration has to be anti-parallel. At least the parallel component is anti-parallel. Whoa! Alright, I'm getting ahead of myself here. What happened there? Hold on here. There was a pause that I did not execute properly. Let's back up. Pause. There we go. Okay, so as I was saying, slowing down, the parallel component is actually anti-parallel with the velocity. Unlike when I'm speeding up, the parallel component of acceleration is in the same direction as velocity. Now let's draw the perpendicular component, and remember the perpendicular component changes direction, and it's always causing the velocity vector to curve in. So I want the perpendicular component of acceleration to point in towards where I'm curving. So I want to point it this way, and then I want to point it this way, right? Because we are following a curved path that's curving in towards this center point right here. And I've decided to go ahead and connect these tail to tip, or tip to tail, excuse me, or tail to tip, I'm sorry, that was right the first time. Tail to tip because I want to actually add these two vectors together to get my total acceleration. Right here, I am now transitioning, I finished curving in towards this point, and now I'm going to be curving in the opposite direction. So even though I didn't have a parallel component here, I do have a perpendicular component because now I see that I'm going to spiral in this way. So I do have a perpendicular component of acceleration right there. And I continue to spiral in, so I have a perpendicular component there and a perpendicular component in right there. Okay. Well, if I add these two components of acceleration, that's going to give me my total acceleration vector. So let's draw the resultant vector. I go from the start to the end. From the start to the end. That one's just one vector, so the total acceleration is the same vector. Start to end, start to end. Okay. And those blue vectors are my acceleration vectors. Okay. I want to end this by actually erasing those acceleration components so you can actually visualize what the velocity and acceleration vectors look like on their own. So here I go, doing a little erasing here. There we go. So now you can see what the velocity and acceleration vectors look like on a general path. Okay, physics students, I'll look forward to seeing you in class pretty soon. Bye.